Hi, this is Kyle. Lab 2 motion of a falling object. The goal of this lab is to track the motion of a falling object and compare the data to a model created through Python. I used a homemade stress ball, a balloon filled with flour that I measured to be 0.0539 kilograms as my falling object. The physics ideas used in this lab were Newton's second law, which is Vf equals Vi plus F net over m times delta t. And because I'm dropping the ball, the initial velocity is approximately 0. F net equals mg, and so Vf equals g times delta t, roughly. And the equation to measure the position of the graph is Rf equals Ri plus V delta t. I chose the ball as the system and the Earth as the surroundings. Here you can see a free body diagram of the stress ball. The drag force, which is air resistance, is pointing up, while the force of gravity is pointing down. Here is the motion of the ball in tracker. As you can see, I dropped the ball in the negative y direction, and the graph of the position versus time graph is here, and it's parabolic, and then the data table is here. And then let's look at the code. As you can see, the predicted graph is also parabolic. Predicting the motion. I chose the system mass as 0.0539 because I measured that, and the ball position vector is initially negative 0.008, like that in tracker, and the initial velocity is 0 because I dropped it, initial time is 0, and yeah. Other things, I set delta t to be 0.001 because the smaller the delta t, the more accurate the calculations, and I set g equals 9.81 because that is the g on Earth. And then here we can look at the while loop, and I set t to be less than 0.567 because that is the last time stamp on the table. And these are the equations. W equals mg j hat, and force drag equals negative bv, and F net equals weight plus force drag, and the ball dot vel equals ball dot vel plus F net divided by ball dot m times delta t is Newton's second law in code form, and this is the position equation. And now let's look at the model. The model underpredicts the motion of the object, which is surprising. I hypothesized that the model would overpredict the motion because there's air resistance in the observation that is not accounted for in the model code. But once I looked at this, I decided not to add in the drag force because it already underpredicted the motion. One possible explanation could be that the object motion in tracker was hard to pinpoint in each frame because of the motion blur, and I may have consistently overestimated the motion of the object. Conclusion. What does it mean? The velocity versus time graph should be a linear negative slope because the acceleration due to gravity is constant. The v versus time graph with drag force is shallower slope than of the one without drag force because the acceleration is slower due to drag force. And what if? If the object was initially thrown down, that would give the model an initial velocity. It would be as if you started the graph at t equals 0.1 for a second. It would not change the terminal velocity. And that's about it.